Good afternoon, everyone, and thanks for joining us for our student poster presentation. I'm particularly excited about this. My name is Danny Welsh. I'm the Dean for the School of STEM at the American Public University System. And we are joined today by three students who are going to tell us about their work. We were supposed to have four, and the fourth one might join us. We hope that that happens, but if not, we'll have a little bit extra time for questions and discussion at the end. Our first presenter today is Glenn Gordon. Glenn is a third-year doctoral student at American Public University System in Strategic Intelligence. And Glenn has a very interesting topic. He's going to tell us about the role of brain-computer interfaces and enhancing astronaut performance in space operations, which I think is fascinating. And it really ties in with some of the stuff that we just heard about in a talk just a moment ago about usability of habitats and environments in space. And I really think that Steve's talk or Glenn's talk might really hit on some of those themes. So Glenn.
Okay, thank you very much. Let me share my screen. One second. Are you able to see anything yet?
We see a black screen and your mouse, but no slide. It says
Okay.
End of slideshow. I just think you're at the end.
Okay.
Try again and click back one. You should have it.
Okay.
There you go.
And
Okay.
Glenn, we can go lacking Laura. If she does not show, we can go 15 minutes and then we'll have 5 to 10 minutes for questions. If you need to go 15 minutes, we scheduled 10, but since we have a little more time, doesn't look like it. Feel free to go a little bit longer if you'd like to.
All right, no problem. Once again, my name is Glenn Gordon. I'm currently a third-year doctoral student at American Military University. The subject of my e-poster is the role of brain-computer interfaces in enhancing astronaut performance in space. Specifically, what roles can BCIs play in space operations? For the background, the study investigated the theoretical benefits of brain-computer interfaces, or BCIs, and their potential use by astronauts during space operations. To provide a brief biology lesson, according to the National Institute of Health, BCI's origins are based in neuroscience. Neuroscience is the study of the nervous system, brain, spinal cord, and neural networks responsible for sensory motor functions. The brain is responsible for processing, creating conscious experiences. While neurons communicate information electronically through synapses or cellular connections, neurotechnology is a knowledge of enhancing our understanding of these systems, providing ways to improve them. Examples of this neurotechnology include neuromodulation, or deep brain stimulation used to treat chronic pain, age stroke victims, and reduce tremors in patients struggling with ALS, for example. Neuroprosthesis can restore lost sensory, motor, or cognitive ability. However, the primary focus, brain-computer interfaces, or again, BCIs, can read, write, as well as transmit information to and from the brain. The term neuro-ST is a merging of both neuroscience and neurotechnology, both disciplines. So we go to the definition. BCIs allow users to communicate external devices using brain signals rather than the brain's normal output pathways of peripheral nerves and muscles. Sounds pretty complicated, but I'm going to simplify it for you real quick. Basically, the devices can perform direct communication with computers and control robotic systems without the need of physical interaction. There are 3 types of BCIs. You have your invasive, which require surgery to implant electrodes into the brain, providing a strong signal. You have BCIs that are partially invasive, or semi-invasive that offer the similar signal strength, but they're placed below the skin rather than directly into the brain. However, both are considerably risky and offer their own unique ethical challenges for astronauts. First invasive and or partially invasive present the potential for infection and the formation of scar tissue. Additionally, this brings up the question of cognitive enhancement, altering personal identity. Lastly, BCIs can also be non-intrusive, such as external halo type devices worn around the head. These devices are for space operations and for astronauts are considerably more cost effective and require obviously no surgery. The non-invasive BCI approach is more suitable for today's applications as it has a more favorable public perception, requires shorter time for qualifications, and is currently safer for the astronauts, which again, to backtrack a little bit, obviously there's no downtime for surgery recovery and risk of infections. All systems share one commonality, and that's training time ranging in the months. And that's dependent on what type of mission the astronauts are training for. Once again, however, this time's not compounded by surgery, recovery, and potential complications and potential complications that are not present in non-invasive BCIs. For the methods or methodology, I chose a multidisciplinary framework, and I looked at 5 specific topics to answer my research question. First one was BCI technology and applications, human-machine interaction, collaborative BCI, meaning imagine a crew of astronauts all equipped with non-invasive or even invasive BCIs and how they can problem solve together as a collective, performance measurements, and ethical concerns. This framework compiled from numerous disciplines using different tools and techniques to approach a problem. Since the field of BCI is rather new, I felt that no single discipline could adequately address this problem. So as far as my research materials, I relied on academic journals, case studies, videos, government reports, and document analysis to review the current state of BCI technology and its applications in the field. Moving over to results. Key findings identified that BCIs could be used to streamline communications, monitor performance, and maximize astronauts' work capabilities. And all 3 of these areas I'm going to focus on briefly. Regarding communications, BCIs may allow users to communicate silently, and hands-free in team setting without the need of cumbersome equipment. Some scenarios where this may be beneficial include the conservation of oxygen in situations where this may be paramount. Traditional communications may have failed, damaged, or just strictly inoperable, or an astronaut may have sustained an injury that permits them or doesn't permit them to speak verbally, but having a BCI connected with other astronauts having BCIs, they could still communicate effectively. Regarding human performance, the use of BCIs has the potential for nearly instantaneous decision-making and problem-solving capabilities. It involves approaching situations from different perspectives, promoting creative and flexible solutions, or what we call now 3-dimensional thinking. And this 3-dimensional thinking incorporates broadening, deepening, and shifting. And to touch on those briefly, broadening explores various characteristics and perspectives associated with a specific problem. Deepening uncovers concepts and assumptions of the underlying problem, while shifting approaches the problem from a completely different context in its original setting. Using the example of collaborative decision-making, BCIs can facilitate the sharing of information ideas among a crew of astronauts, enabling them to work more effectively. This technology can also be used to monitor the cognitive states of the astronauts. So, for example, um, you can manage or monitor an astronaut's attention span, their vigilance, how susceptible they are to fatigue, and also how susceptible they are if they are fatigued, how likely they are to make mistakes. Lastly, regarding work capacity, tasks like operating exoskeletons without gravity, interactions with robotic systems and controlling computer systems through a space station or even a ship can be achieved with BCI. Dangerous tasks like spacewalks can now be replaced by drones and robots under the guidance of an astronaut safely inside the space station or space vehicle using BCI. Think of using BCI to monitor numerous computer systems simultaneously, but you're still freeing up that astronaut to complete other tasks. Astronauts may no longer be bound to, say, their workstation, their panel, or even the commander's chair. Lastly, the potential for BCIs to assist astronauts with problem solving, even while asleep, is another possibility. I'm sure everybody's heard the term, I'm going to sleep on it. Through purposeful dreaming, BCIs can bring about problem solving. Another study from the National Institute of Health states that sleep has been shown to facilitate problem solving with certain sleep stages. Some studies have even demonstrated that sleep can be manipulated to direct problem solving capabilities toward finding solutions that aren't normally achievable while the person's awake. In conclusion, BCIs hold significant potential for enhancing complex decision-making in space operations by improving both cognitive and physical capabilities. Astronauts already face numerous unseen or unforeseen hazards while operating within the space theater. In her article, Samantha Colangelo, Brain-Computer Interfaces for Space Operations, she listed hazards as radiation, isolation, distance from Earth, micro and reduced gravity as a general concern, and non-conducive in hostile environments as a concern for astronauts. It was proposed by Kleins and Klein in 1960 that altering a human's bodily functions to meet requirements of extraterrestrial environments would be more logical than providing an earthly environment in space. But until technology advances, for now, merging BCIs with humans may be the only option for sustained space operations and eventual colonization within our solar system. Again, my name is Glenn Gordon, and this was an e-poster about the role of brain-computer interfaces. If anybody has any questions, I'd be glad to answer them.
Thanks, Glenn. That was fascinating. I will jump in with the first question because I have a microphone.
Okay.
Have BCIs been used in space travel or space exploration before?
Currently, all the articles, and I cite them in the references in the QR code. A lot of the potential uses for BCIs in space are, I guess, a drawing board or theoretical. However, as far as here on Earth, BCIs, if you're familiar with Elon Musk's Neuralink project, back in May, it was approved for the first FDA trials for humans, and I believe there was an article either yesterday or actually this week stating that it was actually going to go ahead with the volunteer. So as far as space itself, no. Nothing that I'm aware of that's currently in space right now. Everything is theoretical of what it can actually do and how it can benefit astronauts.
Do you have an idea of what the development time frame might be like on this technology?
So I'm going to just give my personal opinion. So once again, I don't know how long it took for Elon Musk to get his Neuralink approved by the FDA. I believe it was years. So him doing that has broken down a lot of barriers for, if it is potentially successful, for other companies to propose their ideas to, say, NASA, or even for Elon Musk and SpaceX to do their own version of Neuralink specifically for astronauts.
Right. And I think I stole a question that was placed in the Q&A that I just saw from Riley Johnson. Are there any current successfully operating BCI integration cases? But I think you've already answered it.
So as far as, I hate to keep referring back to Neuralink, but as far as human trials, as far as medical purposes, we don't know yet, besides what they claim the successes are. But however, in one of my references, there are students in the University of Arizona, and a video I posted as well in my references for University of Florida, where as late as almost a decade ago, students in their robotics discipline basically were already flying drones using non-invasive BCIs. So the technology is there. It is possible. It's just actually implementing it and incorporating it into space operations.
Yeah.
But as far as it being, it is not fiction, as far as something that's just off the drawing board or something you see in a movie. It's actually, the video is maybe 10 minutes, and it's very interesting. I couldn't believe it was 10 years old.
That leads into another question from one of our department chairs, Dr. Frank Apaya. Have there been any simulation studies to support the theoretical approach, especially focused on peer-reviewed work?
So is it, just let me try to see if I understand the question. So peer review work as regards to BCIs in space or BCIs in general?
I think simulations to support the theory that these things could work. Like often things are modeled in a mathematical sense before they're actually built, or in this case, maybe drilled into somebody's head in a physical sense. So has that work been done?
I know it has been done. I'm trying to remember the exact reference where they did. I hate to use the word wargaming because that's not what it was called. Basically, it was gaming or simulations as far as the effectiveness of BCIs and what they could do. But there's also other factors they had to consider before they just hand this over to astronauts and say an environment with 0G, or an environment where astronauts are obviously exposed to more radiation than the average person on Earth.
Okay,
That's a good
and
question. I would have to actually review that more.
Sure.
But I know there has been work done, and I believe I know it's in one of my sources as well.
We've got about 1 or 2 more minutes, but there's one more question from your research. Have there been any negative implications that could emerge from using this technology?
Okay, actually, yes. So initially, I reviewed this technology for being an Intel major, the use of BCIs in intelligence collection. So what I will say is, from an ethical standpoint, having an invasive BCI, obviously in somebody's brain, you start running to the ethical questions of, are that person's thoughts now their own? Who is monitoring those thoughts? Obviously, if one of these BCIs malfunctions in somebody's skull, and the question I asked myself is, when I started thinking about it, is, if you have one of these BCIs, especially if it enhances, say, your ability to make decisions on an exponential level, are you considered, I'm not saying are you considered human, but is that ethical? Like, how can you be placed or compared with somebody else now? You know, naturally gifted with intelligence versus somebody that's boosted with intelligence by external means. There's a lot of ethical considerations that go into BCI that really weren't addressed in here.
Yeah.
But there's a lot of ethical dilemmas with BCIs.
Well, Glenn, thank you very much. That was fascinating, and it's not technology that I had been familiar with until this point, but it's certainly interesting.
Thank you.
I'm going to turn it over to Dr. Ed Albin, our department chair for space studies, and he's going to introduce our next speaker. Ed?
Thank you, Danny. That was very fascinating, Glenn, and the previous presentation. And I was really happy to hear you mention Neuralink and the correlation between Elon Musk company Neuralink and SpaceX really supports your research and is fascinating. So I think we're going to see much more of the BCI in space, especially with SpaceX. All right, our next speaker is Steve Deemers, and Steve is a graduate student in our Space Studies program. He's currently working on his master's degree in our brand new concentration called Earth and Planetary Sciences. And this really makes sense for Steve since he is employed as a cartographer specializing in GIS. And I'm really interested to hear about his study, having as a graduate student way back when the crust was cooling on the planet, having studied Mars and the geology and geography of Mars. So Steve's presentation is called A Spatial Analysis Research Proposal for the Water Ice Distributions of Earth and Mars. And it looks like your great looking poster is up there. So I'll hand it off to you, Steve.
All right. Thank you so much. Yeah, again, good afternoon. My name is Steve Deemers, and I'm a career cartographer and geographic information systems, or GIS analyst in Sacramento, California. And I've recently begun the master's program there at American Public University. And I love that that is a new concentration now, Earth and Planetary Sciences. I was excited to be one of the first to jump in on that. And our most recent course, we were assigned with writing a research proposal in comparative planetology. And of course, as a geographer, I wanted to propose a spatial analysis and do something at a global scale. So I chose to propose the spatial comparison of water ice distributions on Earth and Mars. And this is that paper converted to a poster. So there's a lot of words on this poster, and I'll try to zoom in the best I can. So in my review of existing literature on the topic, I found a wide array of techniques and discoveries that were related to the spatial distribution of Martian water ice. And there were a few that were more significant to this proposal that I'd like to zoom in and highlight quickly. So first on the left, this is the Mars Odyssey orbiter hosted a neutron spectrometer that could measure the abundance of hydrogen in the upper meter of the surface. And so this analysis from Feldman 2004 interpreted those measurements as a mass percent of water equivalent hydrogen. And they produced this global map of water ice distribution. Now, clearly there's a high correlation with latitude here that we can see. And this study concluded that in these higher latitudes here shown in blue and purple, the upper meter of Mars regolith may be more than 50% water ice, which was stunning to conclude. And so a few years later, that conclusion was able to be put to the test directly with the Phoenix mission. So in the center there, the Phoenix lander landed at 68 degrees north latitude, well within that blue line. And it was equipped with a scoop that could directly excavate the surface. And these photos, which I'm sure many of you seen before, they were very well publicized at the time, rightfully so, show this white substance being exposed with the scoop, which then sublimated away in the thin atmosphere in just a few Martian sols. So a pretty strong confirmation there of near surface water ice. And then more recently, the photo to the right, I think you can see that there, that photo on the right, that is from the Mars Reconnaissance Orbiter's context camera. And it is showing water ice being excavated by meteor impacts. So this was analyzed by Dundas 2022, and this impact was only 35 degrees north latitude. So at that time, this was the lowest latitude crater showing evidence of freshly excavated water ice. So even as low as 35 degrees, there was still water spewing out of the ground here. So very exciting. Now, those both, the Phoenix and the impacts, those are just isolated surface excavations. But if we wanted to go deeper, this 2016 study by Sturman et al. Used SHARAD, which is a ground-penetrating radar instrument, also aboard the Mars Reconnaissance Orbiter, to investigate this large area here on the Martian northern plains. And this area they had noticed was exhibiting some geomorphological features, some scalloped depressions and polygonal terrain, which are surface evidences of subsurface ice. And so they wanted to analyze this area, and they used SHARAD, and they analyzed these 600 radar grams. That's these kind of purple swaths you see here on the map. And these swaths are about 1 kilometer wide, 3 kilometers long, and a few hundred meters deep. So it can get pretty deep in that analysis. And their conclusion was consistent with 50 to 85% water ice composition, which is a calculated water ice just in that study area of 14,000 cubic kilometers, which is a ridiculous number. For comparison, that is a greater volume than what you would find in Lake Superior, which is only 12,000 cubic kilometers. So a lot of ice under the surface of Mars. So all of those are showing evidences of water, but they're only showing us pieces of the overall story of Mars, right? Only in the upper meter, or only in those limited radar grams, only at a fresh impact site, or at the landing site. So where's my mouse? I'm going to pan over. The goal of my research proposal then is to look at the water distribution on Mars globally and comprehensively, instead of these isolated patches, by trying to leverage something we already know about water distribution by looking to the Earth as comparison. So this map of permafrost distribution by Obu et al. In 2019 shows very clearly the correlation of water ice with two factors. Pretty clear on this map, increasing latitude and increasing elevation. And of course, that's exactly what we would expect. This is because increasing latitude is really just a proxy for decreasing temperature. And increasing elevation is a proxy for both decreasing temperature and decreasing pressure. So the first step I would want to do is to plot a significantly large number of surface pressure and temperature measurement pairs onto a simple water phase diagram, both for Earth and Mars. So this is just a simple diagram. I hope you can see it there on the right. Just showing the approximate locations of where Earth and Mars would land on that plot. But plotting these measurement pairs would allow us to determine the latitude and/or elevation where these water phase transitions might occur. So we see, obviously, Earth phases between freezing into a solid and melting into a liquid, and increasing elevation, which would be down and left on this graph, decreasing temperature and decreasing pressure. That phases very clearly from liquid to solid, and that's because that direction goes perpendicularly with the phase transition. So it very cleanly phases from liquid to solid. But for Mars, you can see that this is actually a little bit ambiguous, and this is what I would want to pick apart with the GIS. Water on Mars phases between sublimating into a gas and depositing back into a solid. But increasing elevation, again, remember that's down and to the left on the graph, that actually follows parallel with that phase transition line between gas and solid. So it's a bit ambiguous then if increasing elevation on Mars should increase the ice content because of the decreasing temperature, or if it should decrease the ice content because it sublimates away in the decreasing pressure. So my first GIS analysis would be to perform a raster calculation between those two surfaces. The first being that water equivalent hydrogen surface from the Feldman 2004 paper. And then the second would be a digital elevation model. So I would use the elevation measurements from MOLA, the Mars Orbiter Laser Altimeter. Those two together would then pick apart some of the irregularities between those. The MOLA dataset and the Feldman paper, they don't use the exact same resolution, so the MOLA data may need to be resampled to match that spectroscopy data, and there's good GIS tools that'll do that. But the goal here is not to just come up with a single correlation to say, yes, it correlates, or no, it doesn't, or it's a weak or strong or positive or negative correlation, but rather to map this spatially over the surface. So where do we find ice distributions that do correlate with increased elevation? Where do we find ice distributions that do not, and why? So asking these questions, as research often does, it leads to more questions and more opportunity for further research and exploration. And as I expect, there'll be lots of confounding and complicating factors that defy a clean correlation across the surface. So the first of those complicating factors we've already seen in the review of the existing research, which is the contribution of surface depth to this analysis. So you can't just take surface measurements. There's a depth to this as well. I was shocked just a few weeks ago, as I'm sure many of you were if you saw the temperature readings from India's Chandrayaan-3 lunar lander and rover. It measured that just in 10 centimeters of lunar regolith, the temperature drops from 50 Celsius to -10 Celsius in 10 centimeters. Now, of course, that's the moon, not Mars, but it really does highlight that the temperature gradient from surface depth may actually play just as significant a role, if not a greater role, than the temperature gradient we get with latitude or with elevation. So this is really adding a third dimension to the mapping analysis as we consider depth. And then additionally, it's worth noting these temperature measurements that we would get on both Earth and Mars are going to vary daily from day to night and seasonally from summer to winter. So there's certainly a temporal aspect to this as well, which now adds a fourth dimension to the analysis. One last thing I do want to point out here on this simplified pressure temperature diagram is the expected Mars measurements get very close to the triple point, or water's triple point, where temperature and pressure allow liquid water to exist on the surface. In fact, the highest pressures and the highest temperatures on Mars are high enough for water to exist on the surface, just maybe not at the same location or at the same time. So this is begging for another GIS analysis. Taking those same points, those pressure and temperature measurements, and spatially measuring them across the surface, calculating and mapping those regions that may have sufficient pressure for water but not temperature, or sufficient temperature but not pressure. And I'm very curious how those two regions come close to spatially overlapping, and how those might vary in the daily and seasonal temperature cycles. So zooming back out again to the whole thing, this certainly does seem like a lot of analysis to propose, but as a geographer, I feel a bit cursed by this need to zoom out and try to see things in more context. The goal would be a broader view and understanding of global spatial trends on Mars, which could then be used to identify specific anomalies for further research and exploration. So thank you for your time, and I can stay to the end of the session for questions if you'd like.
Okay, thank you so much, Steve. And we do have a bit of time here for questions. And as with Danny, since I have the mic, I do have a question for you, and it's something that is a bit of a curiosity. Of course, on Mars you have water ice at the poles, and then residual water ice, and then the carbon dioxide ice caps that vary with the seasons due to the sublimation of the CO2. But my question for you, your presentation got me thinking about these really big volcanoes on Mars, like Elysium Mons and Olympus Mons. And my question is, because of the huge altitude, for example, Olympus Mons is 3 times taller than Mount Everest. Why do you think we do not see ice or carbon dioxide on ice caps on those big volcanoes?
Yeah, that's right. I think it's exactly because of that kind of diagonal phase transition there on that chart. So you look in the Feldman poster, it's a little hard to see here because they've got some terrain shading there, but the Tharsis volcanoes there do not have increased water content, at least in these measurements. And it might be, yes, the temperature is decreasing as you go higher into those elevations, but the pressure is also drastically decreasing. And so the water is sublimating into the atmosphere, and there's no way for it to hold on to that. It's really those low elevation, high latitude areas like the poles where we see the most water. And I appreciate that you brought up the CO2 caps. That was the one thing I was desperately trying to avoid in my research is straying from water into CO2, because that's a whole nother thing as well with its own phase diagram. But yeah, you're right. The tops of the volcanoes don't seem to have those glacier water that we expect to see or that we see on Earth. Yeah.
Very good. We have a couple of questions in the question and answer box. Frank Appa is asking, given the many factors that influence the outcome of the correlation, would it be helpful to condition your outcome on all of these features to account for confounders?
Right. Yeah, you would almost have to do them one at a time, just because there are so many possible confounds here. So it is a kind of a step one. What do I come up with? What are the kind of the outliers? And then a step two. So that's not something I've thought through too much in depth, but trying to attack all of the factors at once probably would be folly.
Good point. Another question from a part-time faculty member in space studies, Michael Zielhofer, and he says this was excellent. And he's asking, have you looked into how the obliquity cycle has affected the movement of water ice, as we have seen in previous studies, as where there has been evidence of past glacial and fluvial activity found within impact craters and at lower and mid latitudes?
Yes, thank you. So when I'm doing the research on kind of existing papers, those kind of Milankovitch cycle processes come up quite often. And there's, another factor to consider, that the water could have been implanted there when obliquity was different, when other types of factors were different. And so the goal would probably be to compare what is now elevation to what we're seeing in the neutron spectroscopy, which is happening now. So and try to get as many layers as I can. But the Milankovitch cycle things were another confounding and complicating factor to this, for sure.
Very cool. And let's see, we have one more question by full-time faculty member in space studies, space and earth sciences, Christy Drexler. She's asking, well, first she says, great presentation, Steve. And she is asking, what are the implications for your findings here? And she wants to know for both the Earth and Mars explorations. And also she's curious about how and why you chose this topic.
Okay. So first of all, I don't have too many findings yet. This is really just a research proposal. I haven't actually tackled it yet. But the implications there, I think, actually do have a lot to do now. More this now correlates back to the theme of this conference, which is exploration. And you know, these islands in space. Mars maybe is the distant continent in space, but human civilization has always been laid out, and human urbanization has always been laid out by its access to water. And that has always been true, and I think it always will be true for Mars and for any landing on any other surface, that a future human colonization, future human map will be drawn by its access to water. And so there's a significance there as to where do we send our landers. It's really a roadmap for human colonization once we find access to these water resources. You know, Elon Musk, who's come up several times already in this conference, his preliminary landing sites are up in Arcadia Planitia, up at, you know, high 60-degree, 50-degree north latitude. Those are the areas where he's looking to be able to have access to water, but also be low enough where we can get good solar energy near the equator. So there is kind of a balance, more water, but also more solar energy. You need to find a nice sweet spot. So knowing where water is, I think there is an implication to human exploration and human colonization on Mars. And what got me interested was, I guess, the last part of this question was, again, maybe just the curse of being a geographer. I really respect scientists who can, you know, focus on, you know, a single charade radargram, but I always feel like needing to kind of go out a little bit further and see things in these kind of bigger contexts, which then just ends up being a lot of data to have to analyze. And I do understand that as well.
And Steve, we have one more question for you from faculty member Arnold Nikosian. Arnold is asking, can you extrapolate this information to possible water on the moon, which is a hot topic now?
Yes, I suppose you could. I don't know as much about the moon as I do Mars, but I think a lot of the theories of geography are very similar. I know the moon obviously doesn't have the same axial tilt, so there's differences there. I know the water resources on the South Pole have become very popular in lunar research, and I imagine there are very similar geographic commonalities that you could use for the moon as well.
Fantastic. Okay. Well, we're going to move along. We do have until 5:20, I believe. And we've been fielding questions as we've gone on. Let me make sure. Yep. 5:20. And Danny,
and our last panelist was able to join us. So if it's okay with the PSO folks, that we could just go a little bit longer, we'll let our next speaker go. And then if people want to stick around for a little bit to hear Laura, then you know, hopefully that is an option.
Okay, fantastic. Good plan, Danny. And good to see you, Laura. These things happen, but we're glad you made it here this afternoon. And we're going to go ahead and transition to our next speaker, Melissa West. And Melissa is a recent graduate of APUS in our space studies program, having received her master's degree, correct?
Undergrad, sorry.
Undergrad, okay, undergraduate degree, and will be moving on to working on a master's degree and or PhD. I believe she's going to transition straight to the PhD, which is a good move at Georgia State University. They have an excellent astronomy program. I'm very familiar with it, living right here in Atlanta. So congratulations there. And today, Melissa will be talking about a fascinating topic with the sun being so active. My colleagues and I have been observing some really cool and big sunspots on our nearest star. So her presentation today is entitled A Detailed Examination of Solar Magnetism and Its Dynamo. And I see you have your poster up, so take it away, Melissa.
Thank you, Dr. Alvin, and thank you everyone for taking the time to be here. And thank you for CISA for having me and allowing me to share my capstone project. Magnetism is at the heart of all solar activity, which in turn affects our magnetosphere, giving us space weather. This is especially important as we become a technology-dependent society and expand our space exploration efforts. What I wanted to find out is how the sun's magnetic field is generated by digging a little deeper to get to the root cause. We will begin with some significant historical observations and work our way to the latest science. The early 1800s began our understanding of sunspot behavior, starting with Samuel Schwabe. He was convinced that there was a planet orbiting the sun closer than Mercury. During his 17-year search, he tracked sunspots as they crossed the solar disk and realized that there were periods of high and low sunspot activity. This became the basis for the 11-year solar cycle. Next, we have Richard Carrington, and he was one of the first to make the correlation that solar activity can affect Earth's magnetosphere via geomagnetic storms, thanks to the infamous Carrington event. After recording the movement of sunspots at various latitudes, he also concluded that the surface doesn't rotate as a solid body. It exhibits differential rotation, in which it rotates quicker around the equator than at the poles. Gustav Spohr worked with Carrington and noticed the migratory motions of these sunspots throughout the cycle. Sunspots emerge at higher latitudes at the start of a cycle, then develop closer to the equator throughout the progression. At the turn of the century, George Hale pushed the field to great heights by concluding that sunspots were areas of high magnetism with a bipolar nature and changes its orientation from one cycle to the next. He used a new technique like the Zeeman effect to calculate the strength of sunspots and built his own spectroheliograph to observe the sun one wavelength at a time. A colleague of Hale, Alfred Joy, took note of the inclination angle of sunspots in association with their latitudes. The further away from the equator, the larger the angle was. Sunspot magnetism was revisited in the 1960s with Horace Babcock when he invented the solar magnetograph to directly measure the overall magnetic strength of the sun. During the same time frame, Robert Leighton was applying new procedures like the subtraction method to spot the difference and measure its magnitude. His method, along with Babcock's magnetograph, allowed photographing entire active regions, discover supergranulation, and detect small-scale oscillations with an average time interval of 300 seconds. He opened the door to a new field, helioseismology. So helioseismology is the study of solar oscillations. If you were to listen to the sun, it would sound like a constant humming noise, and that is because there's millions of wavelengths that travel throughout at the same time. Helioseismologists track one wavelength at a time and determine how long it takes for each one to return to the surface. The path of each wavelength reveals certain characteristics of the solar interior. Each layer changes a wavelength's speed and refraction angle, in addition to changes caused by differential rotation. They have varying periods from a couple of days to a few months, and observing them requires long, uninterrupted sessions. These paths can reveal internal motions, composition, temperatures, and layering, like the core, radiative zone, and convection zone. A notable discovery showed that differential rotation continues throughout the convection zone and is halted at the radiative zone boundary. The turbulence from the convection zone against the rigid radiative zone generates a current within the electrically conductive plasma. And it is at this boundary where a new layer was revealed called the tachocline. And here is where the magnetic field is generated. The Babcock-Leighton model is a great representation of how the dynamo works and remains a staple in solar dynamo theory. Babcock expressed the dynamo in 5 stages. At the start of the cycle, the magnetic field is oriented in a north-south position, and as the sun rotates, it pulls the magnetic field lines around the sun thanks to the frozen flux theorem. As these lines are being pulled, they become intensified, and at the same time, the motions of the convection zone twist them, further strengthening them and turning them into flux ropes. Helicity within these ropes serves as a conservation mechanism and allows them to remain intact as they travel through the convection zone. Additionally, when their magnetic pressure equals the surrounding gas pressure, magnetic buoyancy is achieved, therefore allowing them to rise. The strongest flux ropes make it through the convection zone and out of the photosphere, forming bipolar magnetic regions or sunspots. Meridional circulation expands the flux ropes to reach higher and higher into the corona. As the spots migrate closer to the equator, the leading spot of one hemisphere will connect with the leading spot of opposite polarity in the other hemisphere, initiating a neutralization stage and the magnetic reversal process. The last stage is the reverse dipolar field, where the overall magnetic polarity of the sun is reversed, starting a new cycle. Leighton's contributions took on a mathematical approach and factored in supergranulation to influence the field's migration, leading the ropes to randomly stray further from their initial points. Getting more specific about the dynamo, the structure of the convection zone really is a complex entity. Starting at the top, you have granulation, which you can see on the photosphere, mesogranulation, supergranulation, and then giant cells. Each convection cell exhibits large, slow upflows and fast, narrow downflows. These downflows create superplumes that penetrate deep into the convection zone and reach all the way down to the giant cells. The entire convection zone acts like a filter for only the strongest flux ropes, considering the average magnetic strength of a sunspot is around 3,000 Gauss. In addition to the large-scale dynamo that encompasses the sun in its entirety, there's also the small-scale dynamo. An attribute of fast dynamo theory suggests that all types of turbulent motion in a conductive fluid can create a dynamo, making it plausible for granulation, mesogranulation, and supergranulation to act as magnetic field generators. This magnetic field is expelled in between granules and is more noticeable when the sun is quiet. The mechanism typically seen during this time is convective collapse, and this is when instabilities form within the flux tubes and causes them to shrink rapidly. This increases their magnetic pressure, and then it matches the surrounding gas pressure, which can increasing their strength to up to 2,000 Gauss. So that's a brief overview of the generation, propagation, and emergence of magnetic fields exhibited by sunspots. Significant contributions by Schwab, Carrington, Sporer, Hale, and Joy commenced our modern understanding of the solar magnetic cycle. The individual workings of Babcock and Leighton were brought together to refine the solar dynamo model, which became integral in the field of heliophysics. Helioseismology bridged the gap between what scientists observed on the photosphere and the mechanisms involved within the interior, including the crucial tachocline. The cohesion of large-scale and small-scale dynamos shows the dynamic nature of our sun, with a multitude of forces, flows, and motions that participate. Heliophysicists, solar astronomers, and helioseismologists will continue to unify each piece in hopes of fully understanding the heart of all solar activity. Thank you.
Thank you, Melissa. Excellent presentation on a fascinating topic. When I'm outside taking my afternoon walks, I have to remind myself when I look up and see the warm sun and its heat on my face that I'm looking at a nearby star. This is a star no different generally than all those other bright lights that we see in the night sky. So it's cool that we have this stellar laboratory in our backyard. And we do, there is a question from Terry Trevino. Terry states, a deeply fascinating presentation and topic, Melissa. And he's asking, do you believe the sun and its recent activity can give us some real issues like the big CME hit? And is it possible for us to use these observations that will allow us to predict the large scale CMEs?
Thanks, Terry. Yeah, there's always talk about protecting against these solar events, especially with with the topic with Gateway and lunar exploration and Mars exploration. There is a lot of active work where scientists are trying to predict find some predictive patterns of what would cause a CME, what would cause a flare. They're trying to model and pick up patterns and see how we can predict these events better.
Yeah, absolutely. They're really important, especially with humanity on the edge of getting back into deep space with Artemis, traveling to the moon and ultimately heading onward to Mars. These blasts from the sun, the CMEs, are extremely important to monitor. And we have another question from Arnold Nikogosian. Arnold is asking about the 22-year solar magnetics cycle. He's asking, is the magnetic cycle constant? Is there a relationship between the 11-year magnetic pole flips to those large solar flares that we're seeing?
I know the 11 years is like an average. It doesn't occur exactly, like clockwork. So obviously, this solar cycle has been more active than what they had predicted. And so they I think that's why it's really important to model these predictive behaviors. That way we're not caught off guard. That's just my opinion.
Absolutely. Yeah, with our modern technology, so much of our technology can be affected by solar flares and CMEs. And Arnold follows up with great presentation, exclamation point. Christy Miller also says, great job, Melissa. And she wants to know what interests you the most about studying our star, the sun.
I think when I first got into it, it was learning about the nuclear fusion process that occurs within the core. I think just the power of it is what attracted me to it. And I know how central it is to learn about our sun because it can be applied to planetary science, atmospheric science. It can be applied to exoplanet science. Like the implications are just many. Like it can just expand out to everything.
Absolutely. Thank you so much, Melissa. And we're going to sort of circle back and transition to we'll hand it back to Danny, who will introduce Laura and her poster presentation.
All right. Hopefully everyone can stick around for just a few more minutes. I know that we're after our time, but Laura was able to join us. Laura is a middle school teacher from Homer, Alaska, but she's recently completed an undergrad certificate in space studies, and she's getting ready to jump into a master's in aerospace science. And more interestingly, and perhaps excitingly, and relative to this talk, she's a member of our APUS Analog Research Group. In fact, she's one of our analog astronauts, and that's what she's going to be talking about today. She's going to talk to us about investigating the effects of time-delayed communication on the crew mission support working relationship. So Laura, take it away.
Thank you all for sticking around too. One of the things about living in rural Alaska is that sometimes your internet goes out and then you don't have any cell phone service. So I appreciate it. And yes, I have been working with Dr. Miller as well on this research as part of the Analog Research Group. And we're looking at communications between mission control, mission support, and the analog astronaut crew. And so our first time conducting this research was on the recent mission ARG-4I, where we had a crew at the University of North Dakota's ILMA habitat, their inflatable lunar Mars habitat. And we had a crew of 3 that were there, and then we had a small crew of volunteers working our mission control. And we used the ECHO communication system, which was developed by a graduate student at UND. And that system allows for us to communicate with the crew and allows for us to have a built-in time delay. So we had a built-in time delay of one way, 20 minutes for the majority of the mission, mission days 3 through 10. Our first couple of days we had no delay, and our last couple of days there was no delay. And we were studying the effects on stress and how communication is effective or not between mission control crew. We had a single point of contact, so all crew questions and information went through one person running mission control, and anybody that needed to be involved from the outside mission control would contact them. So we had a solid schedule of who would be manning mission control each time, and so the crew knew who they were talking to. We had communications protocols in place to help with clear and effective communication. We asked both sides to identify who they were and who they were reaching out to, so like MCC to crew or crew to MCC. We asked them to give a short statement of purpose, what they're asking about or communicating about, and then the action they needed. If it was a request being made, if they needed clarification, confirmation, and then a sign off. We always sign off with end of message so that we know that that was it. This is the chunk of text that I need to pay attention to. And then we had surveys that our crew and mission control were completing at the end of each time delay phase. So they completed it at the end of the day before we switched to our first 20-minute interval. And then we had 2 periods with a 20-minute delay. The first period had a very basic ECHO communication system, and the second period had a little more perks to it and information that could be used. And so they took another survey at that transition point, and then again at the transition point at the end of that phase. And so after our mission was over, we looked through the ECHO transcript of the mission, and we looked at the survey data to get an idea of how messages were being communicated, how effective communication was, and what stress levels crew and mission control were reporting. And so you'll see a few graphs here at the bottom. Looking through the transcripts, we took a particular look at messages that were asking for clarification, either from mission control or from the crew, as well as messages that were asking of confirmation of information. And so we found that during the middle of our mission, the messages needing clarification dropped significantly and then rose again as we got to the end and our period of no time delay. And we found that overall, Mission Control was 3.4 times as likely to have to ask for clarification. We also looked at the percentage of out of order messages, and this is something that Echo can do for us. It will put a little stamp at the bottom of the message if it was sent out of order from the last communication. And so when we saw a drop in messages needing clarification, we saw a big increase in messages that were out of order, which is kind of interesting. And they were twice as likely to occur during the time delay. That's why we see that bell curve there, and twice as likely to occur for Mission Control compared to the crew. We also looked at the messages and the average word count and the message frequency, and we found that the word count trended up over the mission, where we see a big drop in daily message frequency as well. We're also kind of looking at, did the crew and Mission Control kind of learn to put more information in a message, so less messages were needed to communicate that information effectively, and found that overall Mission Control was 2.67 times more likely to have to ask for clarification or confirmation from the crew. And then we compared that to the stress levels and frustration. Our surveys that they were filling out asked about how stressed they were feeling because of the time delay and communicating through Echo, how they perceived the other side might be feeling, were they frustrated or not, and just their overall experience. And something interesting that we found was that overall, the people reporting their personal level of frustration on the Mission Control side, it was the exact opposite of crew, which is interesting. So Mission Control was pretty calm. They felt pretty good the entire time. That's why that low blue line there on that first upper graph. And then crew definitely got more stressed during that time delay phase where we were dealing with a 20-minute delay each way. And then I looked at the level of Mission Control frustration versus the perceived level of frustration. And Mission Control, while they tended to be less stressed and less frustrated, they also perceived the crew to be less stressed and less frustrated. But looking at the crew member frustration, they would get super stressed during that time delay. And they also felt like Mission Control was maybe a little more stressed, but kind of accurate to how Mission Control was feeling. So it's interesting that they perceived Mission Control to be calm, but they were super stressed, and Mission Control didn't see that stress. And then looking at them reporting if they felt that communications were difficult during each phase, we can see that crew was typically feeling a little bit more difficult with communicating back and forth than Mission Control was. So overall, we see pretty low levels with Mission Control. This could be because Mission Control's on Earth, they have more support, they're not isolated. And so it will be interesting as we run this in future missions to see if that trend stays. We also noticed that as the out of order messages reached a peak, the crew was also really stressed at that time. And so I'm interested to see if that continues as well. Is the out of order messaging and having to work a little bit harder to figure out how you need to communicate and what you need to answer, is that causing some additional stress? So overall, I'm interested to see how these opposing trends continue. We will be running this again in our mission that is starting here in a week. And it has a bigger crew this time and a bigger Mission Control. So it'll be interesting to see if these trends continue. As a little bit of a side note, we also ran an off-nominal situation with the crew. So they weren't aware that when it was happening. They knew there would be one, but they weren't aware when it was happening. And we wanted to see how communications went back and forth during that time, what questions were being asked. And surprisingly, the crew was very like, yes, let's deal with it. And they just like took it on and were like typing messages, we fixed this, and now we're done. And so there actually wasn't a lot of questions being asked of mission control because the crew was very autonomous. And so we will be testing off nominal situations in our upcoming mission as well. And we have restructured them a little bit so that crew and mission control have to be a little more reliant on each other to get that important information. So it will be interesting to see too how that affects any stress during those time periods. We'll be running 2 without time delay and 2 with a time delay. So overall, that's our study. This is the first time that we ran it, and there's some really interesting results. So I'm excited to see it. And again, I appreciate you all sticking around. Joys of Alaska.
Thanks, Laura. That was really kind of fascinating, and it's not something that you commonly think about, but it is a very real problem. We have some good questions. Dr. Arnold Nikogosian asks, will the NASA planetary internet currently being developed help alleviate these time delays and the stress associated with them?
That is really interesting. And honestly, I don't know much about that yet. And so now I'll read up on it.
Okay.
Yeah, I'm not sure.
Another question is, can you discuss the need for mission control, distance from Earth, and mission autonomy, especially around the given prioritization that friends and family communication currently has?
Yeah. And so when we're looking at these communications, it's especially important as we're getting into a time where we're thinking about going to Mars and there's going to be a large delay in communication that we don't have so much now communicating with the ISS or to the moon. And so it's really interesting how crew autonomy is going to play out with this. Um, of course, they're going to have a lot more training than our analog astronauts necessarily do right now, and they're going to work through scenarios all the time. In terms of communicating with family, through our Echo communications, each crew member does have a private channel or up to 2 private channels to communicate with friends and family. They're still working on that 20-minute delay when there is one. So if family sends a message, they're going to have to wait 20 minutes for it to get to their crew member and then 20 minutes for a response. So it's interesting to see how families deal with that as well, because it can certainly be a little frustrating not being able to communicate immediately. But we do have that avenue in place for them to be able to talk to their family so that they aren't completely isolated from them. And aside from family, we also do some things with mission control to give them updates on like news headlines for the day or information like that to help them feel a little bit more connected to Earth while they're on Mars.
Wonderful. We have another question from Dr. Kathleen Tate, and she is the department chair for teaching in our School of Arts, Humanities, and Education. And she asks that as a middle school teacher, do you integrate any of your research into your classroom instruction?
That's really interesting. In terms of communication, I feel like that's something I'm always trying to build with my students because being effective with your communication is so important, whether you're on Mars communicating with ground or just communicating with another person, and being able to hold that dialogue that says, this is what I'm asking for, this is what I hear you saying, is huge for reducing that confusion. It's especially helpful as a math teacher, helping them figure out how to ask questions so that I can help them in the best way.
Interesting. And the last question that I can find so far is from Pat Deaver. He is a part-time instructor in our electrical engineering program, and he's asking that as a student at an online asynchronous university, you've probably run into challenges of delayed communication with your instructors. Did you learn anything from this experience that might help you understand or might be relevant to online education and not just space missions?
That's a good question. And again, with the like effective and concise, um, communication. That's huge too. If you're, sending a message to your professor and you're not necessarily going to hear back from them right away, can you make sure to get all of that information in your question into your email in a way that they're going to understand what you're asking for and their response is going to be helpful to you. And it also helps to know, like, especially as you get to know professors, like, oh, they have a really busy schedule outside of this, so they're not going to be able to respond immediately or necessarily that day. So maybe if I think I'm going to have trouble with something, I can just send that email with some questions asking for clarification before I get super stuck on something. That way you're not kind of trapped in as much of a waiting period.
Interesting. All right. Well, I think that wraps up our session. Thank you very much to our presenters, and thank you to Ed, my co-moderator, and thank you to the audience for sticking around for a couple extra minutes. And I hope everyone has a wonderful day, and I'm looking forward to seeing everyone in sessions tomorrow.
Thank you all.
Thank you.
Thank you.
Good night, everyone.
Bye-bye.